Shrikant, you can start recording. Has the recording started, Shrikant?
Yes, sir. Like.
Oh, okay.
Okay, so let me recall what we did last time. So today what we are going to prove is the existence of Monge problem. Solution to Monge problem. Convex constant. So mainly the result of what we are going to discuss is a combination of, I'll discuss two methods. Okay, so the first one is the duality, which is due to Brenier, and later following the same ideas Caffarelli. And I'll also discuss a method using cyclical monotonicity, which is due to method. Yeah. So, and for this, I'm following the original paper of Caffarelli. Okay, so which is much simpler for. The assumptions we are going to take is much relaxed assumption. Okay, so my assumption is the following. So again, C is strictly convex and radial. For example, mod is mod whole power t. So strictly convex. I'm assuming my methods, the initial method is absolutely continuous, the final method is also absolutely continuous, and also they are compactly supported. We will simplify several things, as we will see in a moment, and I will denote X the support of U, Y support of. This is my whole set of assumptions for today. All right. Okay, and remember, so last time we we stated that control H problem is same as this dual problem, right? So in the sense that the increment of C d phi is increment of P d mu minus psi d mu, where this supremum is taken over their respective domains. Okay, just I will recall that here the constant was Py minus psi x is less or equals to Cx1. Okay, and last time we also remarked that if so we saw that the optimal pi exists. Okay, so let pi be optimal for the control H problem. Okay? And last time we mentioned that if psi, if the dual problem has a solution, then we derive certain properties. Okay, so today we'll start from there. Okay? So first we'll show that the dp has a solution. Yeah. Okay. So under the assumption A, so we assume A. These are all the assumptions. Then dp admits a solution. So the proof is essentially artificially, we'll see in a moment. Okay? So as you go, you consider a maximizing sequence. Let psi m, phi m be a maximizing sequence. And so we have the constant, right? Phi my minus psi mx is less or equals to c xy. Okay, so here is the first observation. See, in general, I mean, it looks like it is really difficult to extract the substitutes, right? But the first observation is that we can improve this maximizing sequence. So this is a maximizing sequence. First, we are going to do. So this is, remember, this is the selling price, and this is the buying price, right? So the selling price, this constant tells you that for every y, the selling price at y is less or equals to c xy plus mx for all x. Okay, fix one such y, and this constant should hold for all x. Okay, so and this is the selling price at y, and we are looking for from where should I buy this material, right? So for this side. Okay? Of course, the best possible is the infima, right? You would of course try to maximize your selling price. This holds for all x, right? So you should look for all, I mean the infimum, the greatest work of size, right? So look for all infimum, and from where should we take the infimum? I mean our interest is in the support of it, right? So we are transporting from mu to. So we only take infima over all x which are inside the support, which again I assume that this is compact. It's y plus psi x. And obviously from this relation you see that this is holds for all x, so you somehow increased the selling price. Okay, now we are going to again improve the let's psi m theta. So this is my new definition. This is the new selling price. Now once you have this new selling price, where we will increase the buying price psi m x is equals to psi m cxy x no phi m what is the relation? So this one phi m is phi m theta y minus c x y, and this is the suprema over y in factor y. So just from the same relation, right? So this is the selling price. You group some of the selling price, and this is the buying price. And I claim that this is this actually improves your total profit. Okay, so I'll prove it in a way. So okay, let me prove it first. That is indeed improves the profit. Okay, so again from this relation you see that this is the infimum. So phi m theta y, okay, less or equals to xy plus phi m x. Okay, so and if you take it to the other side, minus, this is less or equals to, and this holds for all y, and if you take the infimum, supremum, then still this relation holds, and this is exactly your definition of psi m theta. So by this plan, what you did is you just somehow increased the selling price and decreased the buying price. Okay, so of course then your profit is increased, right? Phi m y minus psi m x is this or equals to phi m theta y minus psi m theta x. Okay? Now you can ask that, okay, I mean you can just go on, right? But here this is actually saturated. So if I don't know whether you have seen in this identity in convex analysis, if f is convex or maybe any f function, okay, so you take the Legendre transform and it's equals to, if you take the Legendre transform 3x, or I mean you can also state it is convex or and you are semi-continuous, then f is the twice Legendre transform of f itself. The same similar thing is happening here, right? So once after just two iterations, it saturates. So if you start from this one, and if you try to improve the selling price, you don't get anything new. You get the same thing. Okay. Now, what is the advantage of this one? The advantage is that, so here is on fact. C I am assuming is strictly convex, right? So, strictly convex functions are locally discrete. So,
What is this legendary transform?
sorry?
What is this F star legendary transform?
Okay, so basically suprema of x dot y minus x y, and of course you need, and this is over, so this is x star y, so this is suprema over all x in R. Yes, and you need certain properties that superlinearity to make sense of this definition. Yeah, this is right. All right. I mean, so this appears naturally when you try to invert the gradient of the convex function. Okay, so to I'll come to that. Okay, so these are more or less standard. I hope that probably many of you have probably seen this. But anyway, okay, so this is if you have not seen this, just try to prove from the definition. Okay, so if you try to iterate again, so it will you won't get it. All right. Okay, so this is the first fact. It's strictly convex, sorry, not strictly convex. Convex functions are locally listed. And another fact is that if you have a family of convex functions or perhaps Lipschitz functions, okay, and suppose the Lipschitz constant of this family is uniformly bounded by some constant x, okay, and you define the suprema of such family. So of course, it could very well be plus infinity when you don't know, but assume that this makes sense. Okay, so assume that this function makes sense, then it is also just follows from the definition. So once we have these two facts, so for a first fact, see here the family lambda here I am adding over x, and for each x as a function of y, this is a Lipschitz, right? C is convex, therefore by fact 1, it is locally Lipschitz, and therefore on therefore this function is Lipschitz, and as you see there, that is where I'm assuming that x and y are compact, right? So this is compact, so this is Lipschitz. So let us denote L, and Lipschitz constant of C, and this Lipschitz constant over the domain, say here x cross y. X cross. Then from that one, you see phi m are elliptic. Phi m tilde are elliptic. From fact 1 and fact 2 both. Okay, so from fact 1, each of them, from fact 1, each of these functions are elliptic, and therefore by fact 2, when you take the supremum or infimum, doesn't matter. On it is all elliptic. Okay. All right, and so this is where now still, and another fact is that, see, if tilde and if, since I am tilde is also a maximizing sequence, if I add a constant, tilde plus constant, it is also a maximizing sequence, okay? Because I believe we had just adding plus lambda and minus lambda, okay? And therefore I choose lambda m such that you just fix one point, fix one, say x naught, and choose a lambda m such that I m tilde x naught is plus lambda m is 0. All right. Okay, so this is a maximizing sequence. Let me denote it by phi m double tilde. Okay. Now, of course, this is a maximizing sequence. Psi m tilde is elliptic, and psi m double tilde, according to my choice, x naught is 0. And therefore, psi m tilde remains bounded, right? Because it's compact. And similarly, from the definition of psi m tilde, so as I mentioned that it saturates at some, if you take the another iteration, so you get psi m y is infima y plus phi m double tilde is a double tilde. Phi m double tilde is the infimum of psi m double tilde and infimum over x. And once psi m is bounded, phi m tilde is also bounded, and therefore this forms a continuous family, which are uniformly bounded. Okay? So by Arzel's-Colli, this converges to some limit. Let me denote it by phi m and psi m and phi m, psi 0 and phi 0, which is then the desired maximum. Okay? So this is a standard Arzel's-Colli. And once you once this is a maximum, again you iterate and without loss of generality. So again you go through the process. Once you obtain this maximizer, and then without loss of generality, you can assume that your maximizer satisfies tightness minus plus x and 0 y x is equal to infimum by 0 y minus c y in y x in x. All right. Just once you get the maximizer, so again you improve using the same strategy, and you got that you get that that is still a maximizer. So this is the technique. Okay. All right. So the maximizer exists now. Yeah.
So, why is the initial psi and xi Lipschitz? Do you take it like that?
The initial
Initial one?
no,
Initial one
no.
is not Lipschitz. Then why it could be very, even if C is Lipschitz,
Yeah.
psi could be very bad. That makes
No, it's in Y.
No. The infimum is in y.
Variable is Y.
yeah.
So here I'm taking the Lipschitz constant over this domain or x y. Okay. So
Change the sign. Yeah, you just started with the convex duals. Then we need to take these sequences.
if I start with the convex,
You just started with those are they are basically duals to each other now, right?
yeah, but again then you have to prove the existence of such. No. No, I mean, of course, you can iterate.
But let's say I started with the convex dual,
Uh,
and then can I directly show the
no, I mean,
Instead of
so
going-
here I'm using the maximal. See, by improving this, then this.
so then you just show that you can't improve the convex dual, right?
This one.
Yeah, so you
No,
write that.
you can compare with this one. That if star is f triple star. I mean, for any function.
Yeah, so if you start with that, then you can't improve it further, right? After like two steps.
Correct.
So then why can't you why do you have to take like the sequence?
I don't understand. So I mean, this can be compared with this one, right? But I'm looking for a particular maximum, right? So this is true for general. For every function, this is goes. But I'm looking for a maximum.
So we are taking the infimum supremum complexes, right? So there should be one point where the let's say the price is minimized.
Right.
So can I take that as T of X?
Exactly.
So
that is what I'm going to do. So that is exactly what I'm doing. Let's see, by assuming this compactness, the
So
situation.
one more question: why this new constructed function psi m tilde, this tilde function, they satisfy this constant that
That is how I define, right? So you see, this is the infimum, right? So of course, and this is the supremum. So you see, so this is supremum. So psi m is bigger equals to this one minus cxy, and you just so take this psi m this side reverse.
Oh no,
No, I mean, you just need, I mean, right? Okay, so yeah, so we got that maximum, and yeah, and last time we mentioned that if such maximizer exists, then I0y minus psi 0x is equals to cxy. This holds for pi almost xy. So this is proves here. And therefore, for each x, I want to associate a y, right? So let me denote the set ky, kx. So I'm collecting all such y for which this identity holds. So let me call it star holds. Okay, and this is where the strict convexity comes in, and this what we can show. You see, this, one identity is always holds, right? So this one is true for every xy because of the definition, right? But we are collecting a particular y for which the equality holds. So you can think of as these are the supporting hyperplanes for any x. Okay, so let me okay. We say x, okay, we have psi 0y. This is according to my definition. Okay, psi 0y. If y is in that set, psi 0y is the equality holds. That's phi x plus cxy. Right? Cxy. Right? But from the first relation, this is the supremum over all sets. Right? Supremum over this. So the supremum is attained at that point x, right? So the gradient should vanish. Gradient psi 0x plus xy would be gradient should vanish, right? And here, in order to take the gradient, I need that psi is differentiable, and which is guaranteed by the local ellipsis property or ellipsis property of phi naught psi naught. So if x, since it is ellipsis, is differentiable almost everywhere. So if this point x is a point of differentiability of psi 0, then this identity holds, right? And therefore, you see, and therefore by convexity, so this is the identity I wrote last time. Okay, I'm just writing here gradient psi inverse h inverse of gradient psi 0 x. Okay, and so I was telling you that this Legendre transform comes by inverting this operator. Okay, so this you can write as x plus gradient h star the Legendre duality of x. Okay, so you can think it of like that. You see, if f is convex, okay, so you want to invert this operator, right? So given any y, you want to find x for which this identity holds, right? So which is same thing as finding the gradient fx minus x dot y equals to 0. So y is given. You want to find x where the gradient vanishes, right? So if f is convex, right, and this is linear, so this function is convex, and gradient vanishes means it's a critical point. For convex functions, the critical points are only infima. Right? So it has only infima. Fx minus x dot y, right? So given any y, so if you minimize over such point x, that should give you the point, the desired point x, right? And you see, this is up to a sign. This is precisely the definition of supreme Legendre duality, right? And the Legendre, as you can see, at the point where x is attained, the equality should hold, right? Fx plus y is equals to x dot y, right? All right. Okay. All right. So we have for the at the point of differentiability, this set is actually unique, right? So what we proved that under our assumption that this is a singleton set, singleton for almost every x. Okay? So until now, I mean that's what we proved, and our mu is actually almost everywhere, actually continuous with respect to the Lebesgue method. So this set is singleton for mu almost everywhere. Now, with this information, I'm going to prove that it actually pushes forward mu equals to mu. Okay? So then, I mean, this. Now, step 2 is that so we are looking at this set kx, okay, and remember that this is defined. This is singleton for mu almost everywhere, and therefore I will denote this map k. Okay, so this k map is whatever, I mean, single for each x you have this singleton set, which is defined mu almost everywhere. And this is a Borel map. And why this is Borel? I mean, I'll just leave it as an exercise, or maybe, I mean, a set of all such x. This actually forms a Borel set. Okay, so which corresponds to the fact that these are the point of differentiabilities of this Lipschitz function, okay, which is a Borel set, and different point of differentiability. So here you see H is strictly convex. Okay? H is strictly convex. So this is a Borel map, okay? And H is strictly convex. So this map is Borel, right? At least where it is defined, right? And it is defined on a Borel set. So this is actually a Borel map, and this map actually pushes forward is equals to mu, okay? In the sense that I have this density, right? So integral gy, integral hy dy over y is equals to integral h of kx, which is dx. Okay, so this is what my claim is, and the proof is actually quite straightforward. And so I have a maximizer phi naught psi naught. What we are going to do, we are going to just part of the maximizer. Okay, so here this is for h is enough to check it on continuous function. Okay, so we fix one such continuous function, and we just part of the maximizer y plus some epsilon hy, and accordingly I have to get a admissible sign, that is the infima of phi epsilon y plus c minus c. This is admissible then. This is then admissible, and according to the optimality, the value should not increase. The value should not increase in the sense that integral phi epsilon d mu minus integral psi epsilon d mu should be less or equals to integral phi naught d mu minus integral psi naught d mu. Okay, and remember this is just phi naught plus epsilon h, and this is the infimum. Okay, so one thing I can just cancel it out, and then what I get is that integral epsilon h and mu is g dy, and this one I will take it to this side minus here I have psi epsilon x minus psi 0x and fx dx and less or equals to 0. Okay, so this is identity I get, and for positive epsilon I can just divide by the epsilon, and this is the identity I get. Okay. And my claim is that, okay, this is minus, not equal, minus. Okay, so my claim is that when epsilon go to 0, this quantity actually goes to h of kx. So that is my claim, and which is quite straightforward. And compactness simplifies things. We only focus on all such cases, okay, where a case is singleton. All right. Okay. So we know that the identity holds that. So given the x, psi 0x, the identity holds at kx of x, x, right? Okay. And therefore, what I'm going to do, yeah. So from this definition, okay, psi at that point, psi epsilon of x, this is the infimum, right? If I put y equals to kx, this would be bigger equals to phi epsilon kx plus epsilon h of kx. I'm just writing what is phi epsilon and minus c from the definition. So here this is the infimum of all such y. In particular, if I put y equals to kx, we get a equality. And if we just do some calculations, so here it is equality, right? So this term and this term together gives 0x, right? So so I can erase this term, 0x plus this term, right? So I take it to the other side, minus x is equals to this one. If I divide by epsilon, this one. Okay? So if I send epsilon go to 0, we get one side of the inequality, right? And for the other side, what we are going to do, we use the compactness of y. Okay, again, as you mentioned that for each y, for each x, there exists a y epsilon for which infimum is attained. Psi epsilon x is equals to y epsilon minus c x y epsilon, and this is phi 0 of y epsilon plus epsilon h at y epsilon minus c x y epsilon. Now my claim is that as epsilon go to 0, of course y epsilon converge to some y naught, because these are y is compact. And from this identity again, you see, so this is p0 plus epsilon 8, right? And these two together give psi 0, right? Psi 0. So from the definition, we also have psi epsilon x minus psi 0 8 is greater equals to epsilon times maximum of h. So, all right. Right? Okay, so we have this identity. Now, as epsilon go to 0, this guy converts to psi 0 x, and from this guy converts to y naught. So this is p0, p0 y naught, okay, and minus c c x y naught, right? All right. Yeah. This term go to 0. Yeah. All right. Okay, but you see that indicates that so x is fixed, right? So y naught should be in that set kx, right? And which is single term, right? Which you noted by again kx. Okay? So this y naught, the point has to be kx, right? So if I now from here, if I pass to the limit, right? From here, psi epsilon minus, you see this guy gives bigger equals to psi 0, right? Or less or equals to psi. So psi 0 is, so from there we get psi epsilon of x equals to phi 0 y epsilon. Okay. Uh, Please. So psi 0 is bigger equals to, okay.
First inequality should be removed.
Yeah. No. This is fine. Okay. So this is psi epsilon x phi 0 minus, you see here phi 0. So if I combine these two terms, look at the definition. So that is the supremum, right? What is the definition? Psi is the psi is about the supremum, right? Psi is the supremum y minus cxy. So if I combine these two, then this is less or equals to psi 0 x plus epsilon h y epsilon. Okay, so these are also, this is the identity also I have from the definition. If you combine these two, and then if you take it to the other side, divide by the epsilon and send epsilon go to 0, then you get that psi epsilon x minus psi 0 x y epsilon. So here you have this is, yeah. No, this is the supremum, right? You see, always remember the identity. So this is the supremum, meaning that this is always bigger equals to, right? So if you take it to the other side, p minus psi is less or equals to. So we are good. This supremum. Alright, okay. So this, now here if you send epsilon go to 0, this will convert to h of y naught, and y naught is precisely kx, right? So from here, sorry,
Psi is the price, right? That should be infimum.
psi is
Price, purchase price, right? Purchase value.
The supremum is the least of the upper. Lower it the profit.
sorry. Yeah, this is fine. So here it is inequality. So sorry. Yeah. So this is fine. I mean, supremum is fine. Supremum is fine. So I was thinking that why I'm getting bigger equals to. So you see here this is less or equals to. Okay. So it is always the opposite. I mean, if you have any confusion, I mean, selling price should always increase. So it's natural to think that it's supremum, but from the constant, you see it is always the greatest overall. You look at the, I mean, best possible scenario. All right. So this tells you that the map is push forward mu to nu, right? So this identity holds. Now the only thing is that this actually optimizes total cost. So here is the thing. Here again, I mean, we use the duality. Theorem is that if you have any other map T which push forward mu is equals to nu, then the cost what we obtain for K is less or equals to, I mean, any other T. And the proof is again, I mean, just the duality. We just expand these two identities. Okay. So remember, by duality, this is equals to phi 0 y or kx, phi 0 y d nu, phi 0 kx, sorry, phi 0 kx d nu minus integral phi 0 okay. So this is equals to this one, and this one I don't know yet, okay? But at kx, actually, this equality holds pointwise, right? So let me write without the integral, right? at kx the equality holds. X k, right? And at any other point, okay, any other point tx, you should have less or equals to cx. So that is for each x, x is the only point where the equality holds. At any other point, it's less or equals. Now we just integrate with respect to pi. So if we just integrate with respect to pi, d pi, okay, d pi. So what you get here is that, I mean, with respect to d mu, sorry. So, mu, d mu. Now here you see by contrary duality. Okay, so. Okay. So this is the identity I'm getting, right? If I integrate with respect to d mu. Okay, so here I'm not writing the measure. Okay, d mu, d mu, d mu. So this inequality holds. Now here I will use that this push forward mu to nu. Okay? So if I do that, then by definition you see this guy is precisely I0y d nu. This is also I0y d nu, right? Now the left hand side is equal, right? So there is no t. So these two are equal, but the right hand side, I mean here you have equality and this is less or equals. So this quantity should be small, right? And this is what we are planning to do. So this is the proof on Caffarelli here, and this is around the same time. Okay, so result of Caffarelli and Karmakar almost appeared simultaneously, and of course they know about each other's work, but later when they completed their work, they communicated and they came to know about their work. So both of these papers cited one another, so and acknowledged that okay, I mean, yeah. So but Karmakar's paper. So this is much more general, and they don't use one. Okay? So they used some cyclical monotonicity, which I'm going to describe now. And as a result of that, I'm going to put it a proof of Brenier's theorem, which is due to Macan. And okay, I'll explain. Okay, so this is the proof using duality. You see, we use duality. I mean, every now and then. So I just, I mean, duality is I mean, everywhere. We used it everywhere, but we can bypass this duality as follows. Okay,
There
so,
was one question.
Yeah.
So this lemma is Brenier's idea or Caffarelli's idea? This particular. So how is Caffarelli's proof different from Brenier? In that sense?
no, I mean, so Brenier, the idea is that you optimize the dual problem, and on that dual problem, the identity holds, and you take the gradient, right? So this is the main idea, and this is some of the which is, I mean, well known. I mean, you got,
So this is Brenner's. This is already there in Brenner's. The
Yeah,
push
yeah.
forward is equal to this. So this is not Caffarelli.
no.
This lemma has to be there even in the Brenner's mod x minus y square also. The one.
Correct, but not exactly in this form. Okay, so some other form. Okay, so exactly in this form, you can find a paper of which appears before Caffarelli's work.
So is there any reference for how they get inspiration to sort of work out this phi epsilon in that
I
manner?
mean, that is, I mean, so you have a maximizer. So you want to find Euler Lagrange equation, so you part of the maximizer and this part. This is
Right, I mean that is except that the whole thing is so much to us that it's becomes very abstract.
yeah. This problem is so actually this set is singleton. Yeah, that is and right, and which actually gives you this thing. Right? Yeah. But I mean, if you look at the approach, I mean, it is quite a standard. What people usually do.
So where is this absolute continuity coming picture that mu and mu are absolutely continuous?
Yeah, so I mean, almost everywhere. So first thing is that you see this map has to be defined for mu almost everywhere. And this map, in order to define this map, you need that the set is singleton, right?
Yes.
And that we can guarantee when it is a point of differentiability of the potential size zero, and which is Lipschitz, right? So
That's right. If
right.
integrable F.
Yeah. So I'm planning to give another proof of Brenier, Brenier's proof due to Macan, where we will exploit all this. We'll exploit more about this. Okay. So here you see what I didn't. What is hidden is that you don't see the boundary. What happens at the boundary? Okay. And the proof, it is completely hidden. And from this proof, it is not even possible to get the idea what is the main difficulty. Okay, so the proof is quite, became very much simplified by just assuming the compactness. Okay? And because it is compact, actually the potentials what we got, they are actually nice in the sense that they are semi-convex. Okay? So it's, they are semi-convex. You can easily show that. Okay, so they are semi-convex, and therefore they almost behaves like convex function, twice differentiable or and therefore the set where they are defined, the boundary is actually the boundary is quite nice. Okay, but here the thing is that they are defined almost everywhere. So even though we need for it takes say from the definition, I erased it from the definition. The potential we got is actually defined everywhere. Okay? So these things, these complications will appear if we don't assume the compact support. Okay. So here is the idea of cyclical modeling.
So Macan and Dango did not have the assumption of compactness.
No. Yeah. So I thought yes. So this is
So then in that case, the measures have to be then at least square integrable.
correct. Actually not. You will see in a moment. Okay, so you don't need. Actually, we will not. So you need the finiteness of the you need that second movement bound, ensure finiteness of the cost and finiteness of the dual problem. Okay, but if I don't go there at all, okay? So that I'm going to describe next. But the motivation comes from here. So here is let us revisit our convex problem. Okay, so remember that suppose so you are transporting according to phi. Okay, and let us choose a point x1, and suppose you are transporting to the point y1. Okay, and somehow you find that okay, this is not very optimal. I have another location where y2, where I can actually, if I send the mass from here to here, it will cost me less. Okay, so instead of sending it here, so here you are sending one bucket. So you thought you reroute this bucket to here. Okay, so here you have now excess amount of weight. Okay, so instead of there, you send it to here. Now at y2, someplace x2 was delivering to y2, right? So they were already delivering to y2. Okay. So they have to now reroute their one delivery to some other location, y3. So you see, so we are just rerouting one unit. So here you remember, so we reroute one basket to here. So here you have one less what you actually require. Okay. Now the process goes on. And finally, suppose you find a xn where you reroute it to this one. Reroute to this one, and then it becomes a cycle. Okay, so now here you initially you were paying cx1 y1. Now by this, if you reroute, you will get something like we have to spend this much amount of money, right? You are not now paying this one, but this is the one you are paying. It is a little bit bigger. I mean, in the sense that this is negative quantity. Okay, so this is the gain you have. Now, similarly for others. Okay, so I don't know whether you are gaining or not, but at least this one is negative. Okay. Now, for this one, you get see you are reworking to y3 and x2y. Okay, so this is your original and this is your new, right? And so on. And finally, you are rerouting xn to y1, okay, and minus c of xn y. So this is the one your original plan, and this is your new plan. And I am writing how much you are gaining or losing. I mean, these quantities each may be like less than 0 or some of them may be positive. I don't care, but at the same time, I mean, if their total sum is less than 0, then you actually improve your transportation plan, right? So if you started your pi, if your pi or pi is optimal one, then you should not be able to find any initial phi. And so for an optimal pi, this inequality should always be bigger or equals to 0, right? And that means summation c and yi should always be less or equals to summation xi y plus 1. For every point xy for all yi. Now here I'm using the convention that when I equals to n, this is y in plus 1 equals to y1. Okay, so this is the convention I'm using. Okay, so that is the condition for optimality, right? So if it is optimal, then this cannot be possible. So this must hold, and this is what we call the cyclical cyclical monotone. Okay, so a subset gamma Ra cross Ra is said to be cyclical monotone if this holds for every such pair inside gamma. Now, so heuristically, what we described here, okay, so the support of optimal plan, support of phi is a cyclical monotone, right? And that's what we described. But let me just warn you, I mean, here there is a technical difficulty here. The cost has to be continuous, and of course, the total cost is finite. Continuous and cost. Continuity is essential. Otherwise, if there is some technical difficulty, you will get something called it is supported on a or concentrated on a cyclical monotone. Okay, so let us see. I mean, what happens if you consider the quadratic cost transform. Okay, C equals to half x minus y squared. Okay, so if I do this computation, okay, if you believe me, you will get this inequality. yi minus yi plus 1, this is less or equals to 0. Okay, so this is the inequality you would get, and for n equals to 2, what you will get that xi or x1 minus y1 or x2 minus y2 is actually bigger equals to 0. Okay. Sorry, x1 minus x2. x1 minus x2 or y1 minus y2 is bigger equals to 0. That means, so these are the points from where you are sending mass, and these are where you are sending mass, right? So that means their angles should be at least less than pi by 2. Okay? So that is a condition for optimality. Okay, so this, remember this, we will use this later on. Okay, now if you look at in one dimension, this tells you that the map, optimal map, will always be increased, right? So if you send some, suppose So this is the mass. Okay. So let me. For n equals to 1, so this tells you that the optimal map is increasing. I mean, so the relation between this kind of C-cyclical monotonicity and the convex functions was actually known around 70. Okay. So at that time, this problem was still open. And so here we are just Brenier's result came around, I mean, he announced it around 87, but in a small paper, but the details came much later, around 90s. Okay. And these are around the same times, 95, 96. Okay. So, and but this relation between the convex function and this kind of sets were already known in 70s. Okay. So the relation is the following. So as I said that, see, in dimension 1, optimal maps are increasing. Okay. So optimal maps are increasing, and therefore they are the derivative of the convex function. Okay. So the similar thing actually here holds, but that means see if you do you know the subdifferential of a convex function, all those things, and about the cyclical monotonicity of there. Okay, so mainly, I mean, so if you look at F, the convex, okay, convex, and you look at the graph. So basically, and you look at the, so this is we are looking at in Rn plus 1. Right? So this is Rn direction, and this is R direction. Okay, and you look at the epigraph. These are the points where epigraph is the set of all xr if x is greater or equal to 1 in this point. Okay? Now let us consider any such point here. Okay, and suppose it is convex and lower semi-continuous. Okay, so I mean here lower semi-continuity comes only at the boundary. Okay, so if it is defined on Rn, then it is continuous. So nothing to worry about. But here by convexity, I mean that you see if it may take infinite values. Okay, so by convex, I mean here that it is defined on a convex set and outside class in. Okay. And whether this is open and closed depends on whether the graph is it is dual semi-continuous or okay. So basically, I mean at this point it is defined if it is dual semi-continuous. Okay. Now, so this is the epigraph. So you consider any point outside, okay? Say x0, r0. Now this is compact, okay, and you have a positive distance, right? So you can separate it by a hyperplane. Right, and therefore this so the whole graph lies on one side of the hyperplane, and this point lies on another side. Now, if you consider a sequence of such points, for each point you get a hyperplane, and in the limit, what you get is something like fy is bigger equals to fx plus some b y minus 6. So this is the subdifferential of f at x. I'm going to I will define. So you see, I will denote this set by fx. Okay, so the graph basically lies above. So you get something like this one. Right? So the graph should lie above this hyperplane, and this point P is basically normal to that hyperplane. Okay. If you want to be more precise, then basically if you cut it at -1, then the point where it cuts is basically what you get here. P. Okay. All right. So the subdifferential is the set of all such P for which this identity holds. It may be singleton or maybe not. Okay. For example, mod x, at this point you have several hyperplanes. So it graph lies above this one. But for convex function, if f is nice enough, that means if it is differentiable around this point, then this is singleton. That you can always prove. But the convex function is actually the converse is true. Okay? So the subdifference f is differentiable, and all is the subdifferential differentiable at x. Define our f subdifferentiable is singleton. So now let us define this f, the subdifferential of the x, and let us take that union all such points x. Okay, and my claim is that this is actually C-cyclical monotone. Okay, so if you consider, so this we are considering all such x as a graph and pi. Okay. Now let us consider a sequence or a finite many points in this subdifferential, and let us apply the definition. I plus 1 minus I plus 1. Right? So this is true for all I. Now if you sum it up for I equals to 1 to n, then you see this portion cancels out, and what you get is less or equals to 0, right? So what you get is xi minus xi plus 1, I plus 1, this is less or equals to 0, sum over I equals to 1 to n. And this is exactly the same thing, right? Or not? This is exactly the same thing, right? Xi minus xi plus 1 equals to 0. This is equals to 0. Let's take the I minus y plus 1. That is fine. So here, I think this is fine. This is fine. This is fine. Less or equals to 0. Okay. All right. Okay. Okay. So basically, subdifferential is C-cyclical monotone. Okay. So what matters is the converse. Around 70 is actually Rockefeller. He proved that the converse is true in the sense that if I'll just take 2 minutes and stop. So he proved that if gamma is cyclically monotone, or cyclically monotone in the sense of this one, then there exists the convex Watson continuous function such that this gamma is contained in the graph of the subdifferential of this set. And so I will start from here from tomorrow, and that together with some differentiability properties of convex functions, we will prove again. Reprove the Brenier's theorem, and then we will again go forward. We'll study what is the regularity of such maps where the Monge equation will come into play, and that is why we will have intersection with ordinary complement with Agni's.
If it is not the quadratic, or does the Rockefeller theorem apply?
Yeah. Actually, the thing is that so it was very surprising that even for of course it has to be modeled in appropriate sense. The subdifferential has to be defined appropriate sense, and but the whole problem is what is the regularity? You see, convex functions are locally distinct, boundary of where it is defined. And it is defined on a convex set, and therefore the boundary in -185 and so on. So what about C convex function? And it is actually true. it is defined on a convex set. The domain has to be convex. And therefore, whatever we can do for quadratic cos, you can just follow the same approach without any technical difficulties. Proving all those properties requires several things, and that has been accomplished by Ganzo and Mecca. I think I overshot